In the last video, we learned about how side chains of amino acids can become deprotonated, and we went through the process of titrating them to show how that could happen and how it could affect their properties. I have two other modifications that I'd like to talk about in this video, and the first one is the formation of disulfide bonds. This is something that really typically happens only in proteins, or mostly in proteins. So we're going to learn it now and revisit it in our next unit on protein structure. The way disulfide bonds form is you have to have two thiols come close together. So we're going to take two cysteines and bring them and their side chains near each other. Now, when I say we have to have two thiols come together, we can only use cysteines. The reason for that is because you can't use methionines. Those have sulfurs, but they're not going to be thiols. A thiol has to have a free SH on it. Now, if we take those cysteines and bring their side chains close together and do an oxidation process, don't worry about what that means for now. We're going to cover that in much more detail later. But if we do oxidize it, that is, take away a pair of electrons, we can end up forcing those sulfurs to share a pair of electrons, and we end up with a covalent bond called a disulfide. And a disulfide is a covalent bond. It's very strong, and it's not easily reversed like an ionic interaction or a hydrogen bond or something like that. It can be reversed, and that is the process of reduction, where you give back a pair of electrons and restore the thiols on the cysteine. But that's not an easy thing to do. And this strong disulfide bond can stabilize proteins or stabilize protein structure. And like I said, we'll see how that works a little bit later in the next chapter. So that's a disulfide bond. The next thing we want to talk about for amino acids is the process of phosphorylation. Now, we've already talked a little bit about phosphorylation or phosphates. We've done the titration of phosphoric acid. We can take that same unit, a phosphate ion, and place it onto three different amino acids. We can use any amino acid that has an alcohol on its side chain. There's three of those. We can use serine, threonine, or tyrosine. And if we do that and place a phosphate on there, we end up with something that looks like this. Go ahead and just copy it down. It's a little difficult to draw until you get used to it. And this would be called, in particular, phosphoserine. We could do it with threonine and make phosphothreonine, or you could do it with tyrosine and make phosphotyrosine. All of these are important. Now we end up forming a new functional group, and it is called a phosphoester. We're going to learn about this later in the course in some detail. But a normal ester would be a COC double bond O, if you remember that from organic chemistry. This is a COP double bond O, and we should probably make a note of that this is a phosphoester. Again, we'll see that later in the course. What I want to leave it at in this video is the following statement. When we take an alcohol like serine or threonine, for instance, or tyrosine that we see over here, it's polar, but it's neutral. And when we phosphorylate it and put a phosphate group on there, we take away the alcohol and we end up with something that has one or two negative charges on it. So we go from a neutral but polar amino acid to a polar, highly charged, highly water-soluble, and able to ionically interact with positive charges amino acid. So the phosphorylation changes the properties of serine, threonine, or tyrosine to be much more polar and negative charged. We're going to see this, like I said, many times, and it's very important in biology, but that's a good introduction for us now. Let's leave it at that.